Dear students, welcome to today's lecture, and we have reached 5.2.2, and we will show an application in financial mathematics of Gersonov's theorem in this section. So let's get started, and we will do that for a price process, a stock price process, and in a limited time period from 0 to capital T, the end of a financial contract, and it's defined on omega with a filtration script ft t between 0 and big T for the Brownian motion. Now let's consider the following. So the stock price process that we have seen before, the geometric Brownian motion, that is st, t between 0 and capital T, and it satisfies the following stochastic differential equation. dst is alpha t st dt plus sigma t st dwt. And we see two functions here. We see a growth rate, a deterministic growth rate of the stock. So it goes with dt. So this is the mean rate of return, alpha. And alpha is typically considered to be larger than the interest rate, because one would say you would only invest in stocks when the rate of return is larger than putting money on a bank account. And if you put money on a bank account, you would get the risk-free rate of return, which we have denoted, for example, by little r. And here we see sigma, and that is the volatility, the uncertainty, which is connected to the Brownian increment process here. dst is alpha t st dt plus sigma t st dwt. And we know the solution of this geometric Brownian motion. A couple of lectures back, we have derived in detail that st can be seen as S0 e to the power, the integral from 0 to t, sigma s dws, plus the integral from 0 to t alpha s minus 1/2 sigma square s ds. So that exponential process multiplied by S0, stock price now, is a projection for the stock price in the future. And we will work with an interest rate process here. Interest rate need not be constant for a certain time in the future. So let's also see the interest rate process as a stochastic process, and therefore we denote it by capital R here, and not by the little r as we know it, as we have seen it before. And a capital R is ft measurable. It's an ft measurable process. And moreover, based on this capital R, this stochastic process for the interest rate, we define the so-called discounting process. Yeah, and we denote it by capital D, dt, little t between 0 and capital T, and we have seen it, and we denote it by, or it's written as dt is e to the power minus the integral from 0 to t of rsds. Here is our interest rate process, capital R. Now, when capital R would be a constant small r, then we recognize the discounting that we have seen before, that is e to the power minus r t minus t. When we know that we should have €1 at final time capital T, then we end up with this e to the power minus r t minus t that we have discussed earlier. But now we have this solution, so it is based on stochastic process here. So dt is e to the power minus the integral from 0 to t rsds, and the corresponding stochastic differential equation that is easily found, and that is in fact dd, capital D, the change in capital dt is minus rt dt dt. But the first D is a capital D from discounting, and the second one is from the time increment. So we also have the corresponding SDE for the discounting. So what we want to look at is the discounted stock price process. We would want to look at the stock price process as of today, And that is considering the discounted stock price process, and that is DTST. And we have a form for DT here, and recall from the previous slide that we have a form for ST. So S0e to the power, a DW term and a DT term. And here we also have a DT term. So if we multiply the two, you can imagine that we will get an extra DT term and that the DW term stays as it was. And that is indeed what we see. DT ST is equal to S0 e to the power, the dw term from the stock price process, the integral from 0 to t, sigma s dws, plus, and here we get that new term from the discounting term, which is here. So we have the integral from 0 to t of alpha s minus 1/2 sigma square s coming from the stock price process minus capital RS ds. And that is the form of the discounted stock price process. The stock price process in the future as seen from today. A discounted stock price process. And that is the process that we want to consider. Now let's try to get to the SDE for the discounted stock price process, the SDE. And you know how we do that. We used to do that by showing that it's an Ito process, for example, or by Ito's product rule. And in this case, we use the Ito product rule to derive the corresponding SDE. And first, let's look at the Ito product rule. The change in DST, the change in discounted stock price, DTST, the change in discounted stock price. That is first the classical product rule, DT, DST, ST, DT, and then the change in S times the change in D. Yeah, so the discounted change in stock price, the change in the discounting times the stock price, and then times the change in stock price times the change in discounting. Now, if we think of this term here, it's relatively easy to see that that is equal to 0 because the change in discounting, that was a DT term. That was a DT term. So if we multiply that by a DW term, we end up with the cross variation. And if we multiply that with a DT term, we get DT squared, and that was equal to 0. So this term will not give us any contribution in our Ito product rule. We only need to look at these two. And for these DS term and the DD term, we have the expressions from the previous slide, and we can just substitute them. So let's do that here. And that means that this is dt times alpha t st dt, the drift term, plus dt sigma t st dwt. So here we have substituted ds, and we enter up with these terms. And the st dd term, st is here, and the change in discounting was minus rt dt dt, the time increment. So we end up with this form. As I mentioned, this term doesn't contribute anything. We have two dt terms. Let's connect them, the one here and the one there. And we have a dw term. So rewriting this gives us, in fact, so we recognize that there's a ds here and a ds there, and a dt term, of course. So we end up with alpha t minus rt dt st dt plus sigma t dt st dwt. And these are the dynamics for the discounted stock price. We have again a dt term and a dw term. So let's now introduce a function theta, and we define it as alpha t minus rt over sigma t. And we want to substitute that in the dynamics of the discounted stock price process. Well, here you see appearing alpha t minus rt, and if we look at our new definition, you recognize that alpha t minus rt is in fact theta t times sigma t. So we rewrite this function, and here we have theta t times sigma t, and the other parts we just copy, times dt's times st dt. And here we just copy the term that is sigma t dt st dwt. So these are the rewritten dynamics of the discounted stock price. Now we can rewrite this, and then we recognize a form that we have seen before. You see that in this term, we see the sigma t appearing that we can take out of the brackets, and we see the discount term s or dt st. So we take them out of the brackets, so we put them up front here. That is sigma t times dt times st, and what remains is the theta t dt plus dwt. And that term may also look familiar to you, because that was from the previous lecture, that was a dw tilde t term that we had defined in our lecture on the Gerson Off Theorem, that we have defined as a Brownian motion under the p tilde measure. So let's see what we can do with that. First of all, we can just write that like that. If we define this as the change in the w tilde Brownian motion, that would be then equal to sigma t dt st dw tilde t. And the aim is to make dt st, the discounted stock price, a martingale. Well, if we want to do that, we have to make use of the Gerson Off Theorem. So let's see on the next slide how we work with that. We want to change measures. And we need to change measures. We want to go from p to p tilde. And the aim would then be that the discounted stock price, little t between 0 and capital T, becomes a martingale under this new p tilde measure. And to this end, we define our z process, our transformation to the new measure, z process, as we have defined it earlier. So zt is e to the power minus the integral from 0 to t, theta s dws minus 1/2 the integral from 0 to t, theta square s ds. But now we have a specific form for this theta function. Because from the previous slide, we have defined theta t as alpha t minus RT over sigma t. And alpha was the mean rate of return of the stock. R was the risk-free interest rate of the interest rate as a stochastic process. And sigma t is the volatility. This is an adapted process. Now we define again z as z at final time capital T. Script f is the filtration up to time capital T. And our new measure, p tilde of a, is the integral over a of z dp. Or in other words, in differential notation, dp tilde is equal to z dp. And that is, with this definition, equal to zt dp. And we define our new Brownian motion, our w tilde. Now, we don't know yet that it's a Brownian motion, right? That is the part where Gersonov's theorem comes into play. But we define this stochastic variable w tilde t as wt plus the integral from 0 to t theta s ds. And we substitute for theta our specific form that we have written down over here. So that is equal to wt plus the integral from 0 to t of alpha s minus rs over sigma s ds. All right, we have this new variable w tilde. We have a change of measure, p tilde. We have a z that is z at capital T. And here we have our transformation. And then we have Gersonov theorem, and Gersonov theorem tells us everything has here been satisfied. Expectation of this function is equal to 1. It is a non-negative variable. So we have all the setting, and then Gersonov theorem tells us that W tilde T, T between 0 and capital T, is in fact a Brownian motion under the P tilde measure. So we make use of that, and we will rewrite the process, the discounted stock price process between 0 and capital T, in terms of this Brownian motion W tilde. So the change in the discounted process d dt dst, d dt st is equal to sigma t dt st, and then we had that process here, theta t dt plus dwt, and now we can rewrite that as sigma t dt st dw tilde t, and we know that these are Brownian increments. That follows from the Gersonov theorem. And writing this in integral notation gives us, so this is the differential notation again, writing it in integral notation, it gives us that the discounted stock price process dt st is the discounted stock price process at time 0, d0 s0, plus the integral from 0 to t, sigma s ds ss dw tilde s. And here we recognize this is the classical formulation of the Ito integral with respect to the Brownian motion W tilde, and hence it's a martingale under P tilde. So here a lot of our theory, the theory that we have learned from the previous lectures, comes together, and we can say that the discounted stock price process, is a martingale under the new measure P tilde. And what this means is this process is fair, and fair is in the sense that what I know today, so S0, what I know today is my projection for the future. Yeah? When we are dealing with a martingale, we know that the best prediction of the value in the future, so the expected value of the price in the future, is in fact the value now. Right? So in that sense, the process is fair. The best projection for the future is the value today. Now we have written down the discounted stock price in terms of W tilde. Let's see what this impacts for the stock price itself under this new measure P tilde. So let's rewrite the process S in terms of W tilde. So we use the differential dst is alpha s ds plus sigma s dwt, and we have our new Brownian motion dw tilde t is theta t dt plus dwt. Well, from this one we get an expression for dwt being dw tilde t minus theta t dt, right? So this one goes to the left-hand side, and then we can substitute it into this expression, giving us it's alpha t st dt plus sigma t st dw tilde t minus theta t dt. And here we recognize again a dt term times sigma t st, and we can bring it together with this other dt term, and collecting the dt terms gives us, this is alpha t minus sigma t theta t times st dt plus the dw tilde term plus sigma t st dw tilde t. And if we substitute for this one the expression that we know, that was alpha t minus RT over sigma t, we see that the sigma t will cancel out, and also the alpha t will cancel out, and what remains is in fact the RT st dt. So writing this out gives us dst is equal to RT ST dt plus sigma T ST dW tilde T. So this is our price process in terms of the Brownian motion W tilde. This is our price process under the new measure P tilde. And what we see is that under this new measure, so in this fair world, if you wish, then the drift term is replaced by the interest rate term, in fact. So the drift term is replaced by the interest rate term RT. And when we are in the Black-Scholes setting, where RT is equal to small r, and sigma T is replaced by sigma, we see that we have dst is r st dt plus sigma st dw tilde t. And this is a very familiar form that we will see later on. It is the price process under the new measure, under the measure P tilde, and we call that the risk-neutral measure, risk-neutral measure. So under that measure, we will see that we are dealing with martingales. Yeah. So under P tilde, the mean rate of return alpha does not appear anymore. It is replaced by an interest rate process, by the interest rate RT. And then we see, we recognize a geometric Brownian motion, where alpha is replaced by RT. And we know the solution for that one. This has the solution ST is equal to S0 e to the power, the integral from 0 to t, sigma S dW tilde S, plus the integral from 0 to t of RS minus 1/2 sigma square SDS. Note the change here that under this risk-neutral measure, we have this expression. And again, as I mentioned, under the Black-Scholes world, in the Black-Scholes world, when this sigma of t is equal to sigma, alpha of t is equal to alpha, and r is just a constant little r, then we are dealing with the following expression: st is equal to S0 e to the power sigma times w tilde t plus r minus 1/2 sigma squared times t. Because when these are all constants, this is a simple integral that we can just easily evaluate, and the same goes for this one. When this is a constant, then we end up with w tilde t minus w tilde 0, but w tilde 0 is equal to 0. And that concludes the first part for today's talk. It's a shorter one today because I think it's important that you learn in detail the start of chapter 5 and also the chapters 3 and 4. They really need attention. We will be using those techniques all the time. So take your time and learn that. And this is a very nice application of the Gerson Off Theorem in financial mathematics in order to look at stock prices under the so-called risk-neutral measure. After that, we will look at the value process, the portfolio process, delta, as we have seen it earlier, and we will look how that then is under the risk-neutral measure. Thank you for now. See you in a bit.